Question 4 about waves. Some students want to investigate the properties of different waves. Student 1 drops a rock into a pond. Student 2 stands at the opposite side of a pond 5 meters away with a stopwatch. The students and the pond are shown in figure 7. What exciting lives they lead. So here we go, we've got student 1 who is the rock dropper, and we have student 2 who is the bearer of the stopwatch. The rock is going to be dropped. They've actually mislabeled that. Impact rock, yeah, tut. When the rock hits the water, it makes a sound and causes ripples on the surface of the water. Student 2 observes the rock hitting the water. Describe how the students could determine the speed of sound. Well, to do that, you need an equation for speed. So how would we find the speed of something? Well, speed, and this goes back to my discussion of density in the previous paper. If I want to design an experiment, think about the equation you're going to use to work out what you're trying to find out. So, for example, speed equals distance divided by time. Now I know that to find the speed of the wave, I need to know the distance it travels and the time that takes. So, in order to do that, we can say students could measure the distance between rock impact and second student. I believe we already have that actually. It is 5 meters away roughly, 5 meters. And students can measure, and where are we going to get the time? Well, we want the difference in time between the students seeing the rock hit the water and hearing the sound of the rock hitting the water. That will be the speed of sound. Students can measure the time between seeing the rock hit the water and hearing it. And lastly, speed equals distance over time for the speed of sound. That is how they could find the speed of sound. 4.2. Sound is transmitted by a longitudinal wave. The ripples caused by the rock are transverse waves. Describe the difference between transverse and longitudinal waves. Simple answer to learn to these questions. A transverse wave, that's your classic wave, like this. A transverse wave has vibrations or oscillations. I'm going to write, you could write vibrations if you prefer, perpendicular to its direction of travel. So, looking at my diagram above, if this wave is travelling along that way, the vibrations are at 90 degrees to the wave here. On the other hand, a longitudinal wave has oscillations, again you can write vibrations, parallel to the direction of travel. So, In a sound wave, for example, we normally sketch them a bit like this to show areas of stretched out particles and areas of compressed particles. If the wave is moving that way, the particles are vibrating parallel to that direction. 4.3. The ripples cause a lily pad on the pond to move up and down. The students conclude that it is the wave, not the water itself, that travels out from the impact site. Explain whether the student's conclusion is correct. Well, the students, based on their observations, are most certainly correct. Thank you very much, 1 mark. Then what else should I add? Why are they correct? Because I'm being asked to explain. The students are correct because if the water was moving, the lily pad would move with it. It does not. Therefore, it must be the wave moving, not the water. And 4.4. So I can see immediately we've got a diagram of refraction below. And I'm told light waves travel from the air into the pond water. Figure 8 shows how light is refracted, i.e. changes direction as it passes from the air to the water. Explain why the wavefront appears different in the water compared to the air. So we can clearly see the wavelength has decreased as it's gone into water, and it's also changed direction. So why has that happened? Well, what we see up here is the edge of the wavefront up here that hits this boundary between the air and water first, slows down and changes direction, whereas the edge further away over here continues at the same speed for a while. Therefore we get this change in direction. So to explain that, I'm going to say the edge of the wavefront, and when I say wavefront, this is a wavefront, all of these lines as they're showing the direction of those waves, like water waves, like the crests of water waves and what direction they're moving in. The edge of the wavefront that hits the water first slows down because light waves travel more slowly in air than water. Sorry, in water than air. We can tell that as it's bent towards this line here called the normal. How do you remember that? Well, we've got SFA and FST. So if you're bending away from the normal, you're going slow to fast. If you're bending towards normal T, you're going fast to slow. Here we're bending towards the normal, therefore we're going fast to slow. Anyway, back to the answer. The edge of the wavefront that hits the water first slows down and changes... First slows down while the other edge continues at the same speed. Therefore, The slowed down part changes direction and thus appears different. Oh, and the wavelength reduces. So your marks there are for saying that the edge of the wavefront that hits the water first slows down, and then your marks for saying it changes direction as well.